Yeah, um, I'm not sure if the audio is working.
What about now?
Yes.
All right. Now I need to redo the thing quickly, okay? We got a linear system, and we say, hey, before what we're doing is we have a partially decoupled or completely decoupled system. We solve them one by one, right? Now we say, well, we don't have to do that. We just take the matrix, okay? We do the eigenvalue and the corresponding eigenvectors. So this eigenvalue has this eigenvector. This eigenvalue has this eigenvector. Then the solution looks like exactly the form. You put the e to the lambda t here. You put the eigenvector here. So you get the first and the second solutions. Luckily, they are linearly independent. Then by the linear property, your general solution is nothing but k1 times the first one plus k2 times the second one for all possible k1, k2. That's it. You just find all the possible solution of the linear differential equation by using eigenvalue and eigenvector combinations. Sounds good? So all the information comes from this matrix. This matrix determines what your solution looks like. Of course, for initial value problems, you just need to do the simple thing that is, well, if you have an initial value, you basically want to find k1 and k2. We're not talking about any k1 and k2 now. We're talking about one specific pair, which give you the particular initial condition. So what you can do is you can just plug in y0, which is this. So which is just k1 plus k2. And that should equal to the initial condition, which is 2, -3. So from here, you can solve for k1, k2. Basically, you have done this before. It's basically solving a linear system, right? Okay, let's give you k1. I will skip. You can verify by yourself. And k2 equals this. So not only you know it's the general solution with k1, k2 be any number with the particular initial value. What you have is y equals 2t. Okay, that's a complete example of how to solve initial value problems when you have a system. General solution first. The rest will just be initial values. Okay. That's what we had in 3.2, roughly. Of course, we have some leftovers. Okay, we're going to talk about them one by one. Number one, you found two solutions from two different eigenvalues. So you have two solutions, but is there a guarantee that they are linearly independent? The answer is yes, in this way. The eigenvector of distinct eigenvalues are linearly independent. So if you have to, you're all set. Of course, this leaves us a question. What if you have a redundant eigenvalue? What if you have redundant? Okay, this is the leftover. We haven't solved it yet. But in general, if you have two distinct, fine. Second left over, you have e to the lambda t v for all your general solutions. From here, we can see, well, this is basically an exponential decay or exponential growth. It really depends on is lambda positive or negative. Okay, then we kind of have something like if lambda is bigger than 0, we have a source because you basically go away. Lambda is less than 0, basically we have a sink. And if lambda equals 0, we have something before we call node. Let's just leave it, okay, for now. But clearly, we can talk about equilibriums in this way. Okay. Number 3, of course, you have eigenvalue, you have eigenvectors. The eigenvalue will give you positive, negative, or 0 if you have real case, but what if you have a complex lambda? Okay, that will correspond to something called rotation. And finally, what if you have a lambda which is 0? For example, you have something look like this. I think it's not hard to see if you have a 0 eigenvalue. That basically means your determinant is going to be 0. You are not invertible, so we have the degenerate case. Okay, so this is the framework that makes sense, but then we have all these kind of things we need to talk about to make sure that we cover all the possible cases. Because nicely, if you have a 2x2 system, you have two distinct real eigenvalue, then period. But what if you have redundant ones? What if you have 0? What if you have complex? Okay, things can go wrong. So let's go over them one by one, each one taking a section. Sounds good? That's all the cases we will have. Of course, when you have a 5x5 system, it's the same thing. You just care about how many zeros, how many redundants, how many complex do you have. They're basically the same idea. Okay, so let's talk about 3.3 first. Let's talk about we have real eigenvalues. We talk about phase portrait. Real linear system with real eigenvalues. I will add distinct. Okay, so basically for this one, we want to talk about the equilibrium. Particularly, we want to talk about the equilibrium 0, 0, okay, for 2D system with distinct real. So it's very restricted values, eigenvalues. Let's talk about it. Okay. What's the equilibrium? AY equals 0. Okay. What equilibrium do you have? Number 1, I definitely have the trivial one, which is 0, 0. Do you have anything else? It really depends on is this one degenerating, because we have two distinct real eigenvalue. This one's not degenerating, so this is the only equilibrium we have. No anything else. Otherwise, degenerating. Otherwise, we have degenerate system, which we'll put in a later section. Okay. Then we just want to talk about sink, source, nodes, or anything. Well, how do you talk about it? Let's assume we have the phase portrait. We call this X and Y. We already have this thing here. You have two distinct real value. That means you have two straight line solutions. On each solution, straight line, you have e to the lambda t and e to the lambda t for two distinct eigenvalues. Sounds good? All right, let's take one of them. Here's 0, 0. On this one, you have e to the lambda 1t. Okay. So how are you going to draw the arrows like this or that, which tells us source or sink? Think about it. When t goes to infinity, where does this one go? Two choice. It either goes to infinity or it goes to 0. Okay, corresponding to lambda 1 bigger than 0 and lambda 1 less than 0. Lambda 1 equal to 0, again, it's degenerate. We don't consider it. That means if you're talking about ending behavior, when you let t goes to infinity, you're either here or you go back to this one, which means 0. Good so far? So that gives us a very easy thing to check. That is, okay, this one corresponds to this. This one corresponds to this. This is clearly a source. This is clearly a sink. But keep in mind that this only works on this one line. Not everybody, just this one line. On the line. Make sense so far? Now, for anything, you do know that you have two straight line solutions, right? So how many different combinations can you have? Well, there are a source on here, and there are a source on here. That's one possibility. Still okay? Then what about a point here? It's gonna be a linear combination of these two straight line solutions, right? So this one is gonna have a component on here. It's gonna have a component on here. Like we said, the component on this line goes away. The component on this line also goes away. Together, can you see that? As long as the solution leave 0, 0 in two directions, it actually leaves 0, 0 in every single direction because they're nothing but a linear combination of the two directions. Sounds good? Okay, so if both are bigger than 0, we have a source. Now, I don't think it's difficult to see. If both are going in, okay. What about something which is not on the line, which is a linear combination of the two lines? You still come in. Okay, so it's going to be a sink. So maybe. Okay. Now it's very easy to see we have a third case. Source in one direction, sink in the other direction. Or so on these two straight lines, you got the source and sink thing. For anything not on the straight line, you basically have something like this. Make sense so far? Okay, so should we call it a source or should we call it a sink? Do you come back to 0 or do you leave 0? It really depends on which direction you're in, right? Okay, so we cannot call them neither. We give them a name, we call it saddle. So it's settled. For equilibrium 0, 0, we have 3 different cases. Case 1, case 2, and case 3. So I think that was Andrew, right? You asked the last time. Now you can say firmly. If it's less than 0 in all direction, it's a sink. If it's bigger than 0 in all direction, it's going to be a source. If it's part and a part, it's neither, it's a saddle. For 2, it's easy, right? If you have 5, then you have 5 ore coming in, 5 ore coming out, or 1 in, 4 out, 2 in, 3 out, 3 in, 2 out, all the combinations. Okay, by then it really doesn't quite make sense to talk about anything other than saddle. So sink and source are very, very rare. Okay. Everything good so far? Question. Does this name feel all right with you, saddle? Why do we call it saddle? Well, that must be connected with what we had in calculus 3, right? We have saddle points. So if you really think about it, what's going on here is, what do you mean by a source? What do you mean by a sink? That means as time goes by, your potential kind of look like this. So if I just put anything here, what's going to happen? That thing is going to go to here. If I put something here, that thing is going to go to here. It's the same as if I put something here, they just trace all the way back. So it really makes sense for you to think about sink, in terms of a potential like this. If you put a ball, no matter where you put it, it eventually goes to here. Maybe it oscillates a little bit, but eventually it stops here. Sounds good? What about source? That means this thing tends to leave. So you have a high potential here, but low potential anywhere else. So you will stay here if you're just here, but if you move away a little bit, you just drop. Make sense so far? So that's almost like a source. If you just draw the potentials, this does the same thing. So you can say stable, not stable, all the kind of terminologies. Okay. Now, this is only for 1 dimension. What about 2 dimension? That means you are a sink in all perspective, which makes you which makes you a bowl. Because these two, everybody else. Therefore, you basically have a bowl. No matter which side you put your ball on, that thing will actually go down. Even maybe they even spiral in, okay? But eventually, they will stop at the bottom. Okay? If in 2D they both go away, that's almost like you have a bowl, but inverse put. So again, this is going to be a source. Still okay? Finally. Well, that's as easy as in one direction and in another direction. How do I draw this? Here. And how do I draw it? Maybe I draw something like this. So basically have a cap, you have a cup, okay, but they're twisted. See, in this way you make a saddle. Sounds good? So if you sit on saddle, what's going to happen? Well, if you move forward a little bit, you move backwards a little bit, you go back to the bottom. Right? You don't fall from the horse. But if you move to the left and you move to the right, you definitely fall off the horse because that's the direction you're going down. Make sense here? Okay, that's what we mean by a saddle. In one direction, it's like that. In the other direction, you actually fall. Okay, that's where the name comes from. Saddle. All right. Any questions so far? Good. So we have sink, we have source, we have saddle. By the way, you could never have a saddle in one dimension. So saddle is actually new in 2 dimension. In 1 dimension, we only have this and that. We don't have these two. Okay. So everything I just said only works when you have bigger than 2D. Do you wonder why don't we have this? Okay, we talk about like this way or that way. We never talk about do we have a node and then you're in 2 dimension like that. That's normal, right? If you think about it. But now keep in mind, how did you get this? You get it when you have y prime equals, let's say this is 1. That means before 1, after 1, you both have positive, right? Can you see this is not linear? Okay, so you do have nodes, but that doesn't happen for linear constant coefficient case. If you have things like that, your solution won't look like this either. Okay, so that's why we only have these 2 cases, because it's a linear. And because they have e to the lambda t times v. That's why we only have 1 direction. It's either both in or both out. Okay, by the way, this one goes out. This one goes out not because of this t here. It's actually because of your k1 in the front. Okay, so maybe you see something like a both direction, but actually you either have this solution or you have this solution. Okay, because you have a constant here to tell you which direction you should go. So both direction you're going to infinity, okay, but not at the same time. Okay. Now let's see the code. There's nothing particular to talk about there other than just verify what we have. Okay, so first system, we have -2, -2, -1, 3. I calculate the eigenvalue, -4 and -1, both less than 0, so we should have a sink. Okay, let's do it. Okay, the green line and the orange line will be the straight line solution. Now each of them, you go to the middle. Then everything else also goes to the middle. Okay, that's a sink. Second, you reverse everything to be negative. So you have lambda1 equal to 4, lambda2 equal to 1. Both direction you goes out. That means you have a source. Okay, everybody's going away. Finally, you have something which is partly negative and partly positive. So you should have a saddle. Moreover, in the direction of 1, 1. Yeah, actually, it's hard to see which one is 1, 1. Let me see. The green one is actually 11, 6. I should pick something else, but either way. The orange one is 1, 1. Okay, you can see it's coming in. The green one is actually 11, 6. So that one's going out. Okay, together you have something which is like saddle. So you start to see those kind of parabola type of behavior. You go in, meanwhile you go out in another direction. That's when you start to see things bend. Otherwise, you will have a nice curve, which all goes to 0, 0, or all comes out of 0, 0. They never bend halfway. All right. Okay. We have the phase plane. Another quick way to think about it is basically this. You know, you have 1, 2, 0. Okay, y prime equals that. Then clearly you have 2 eigenvalues. Okay, because of the diagonal, and one eigenvalue is 0, 1, and the other one is 1, 0. Okay, so basically you have 2 directions. On one direction you're going out, on the other direction you're going out. Sounds good? Okay. They go out at different speed. So if you take t equals 1, this one is here. This one is probably further. You take t equal to 2, this one is here. This one is even further. Good so far? So if they go out at the same speed, you will see a trajectory look like this. Same speed both ways. Still okay? If one direction is slightly faster, you're going to see something like this. Okay? This is clearly the horizontal is faster and the vertical is slower, but they both just increase at the same time. It's just the x is bigger. Still okay? Similarly, you have the other direction. Maybe this is the case. It really depends on which lambda is bigger. Okay, the bigger one goes faster. That's why you see all the curves. What about eventually this thing changes to something like this? Now you know it's nothing but a change of basis from from 1, 0, 0, 1 to v1, v2. We're all talking about the two-dimensional domain. It's just, do you want to use the original E1, E2? Okay, or do you want to use the new V1, V2, which is just a change of basis? Sounds good? And in linear algebra, when you do a change of basis, basically what you do is you just times a matrix. Remember? Okay, that matrix is what you did for initial value. Remember, when you do initial value, you kind of solve AX equal to B, right? That's the change of coordinate matrix. come from when you have y0 equals k1. We'll plug in t, you just have 1. This will be the change of coordinate matrix. Just in case you want to associate this one with linear algebra. So that's the neat thing about linear algebra is whenever you have some case, you just want to think about the simplest case, which is diagonal. Everything is 90-degree, x, y direction, beautiful. Now, when you try to go from here to some random two linear independent basis, you just times the matrix. Everything is set. Okay, that is good. Meanwhile, you actually can connect this one with the diagonalizable, okay, of matrix. So all these concepts are connected. They're all the same thing. They're all the same thing. Okay, I cannot go over every single details of them. I just mentioned it here. I think you kind of grab the concept. Okay. I keep receiving questions from people about linear algebra is why do we have 5, 6 different ways to understand the same thing? Okay, that's basically what we're trying to do. We understand the same thing from all perspectives: coordinate transformation, linear transformation, linearly independent vectors, number of equations, and number of vectors. Okay, in this way, in all kinds of situations, you will have multiple tools for you to think about a thing. Sometimes one is better than the other. All right. Is everything clear before we move to complex? All right, let's move to complex. Okay, what do we have here? Complex. Let's talk about a system. Okay. Quick calculation. For 2 by 2, we're solving a quadratic. When you solve a quadratic, it's very common for you to see complex numbers. Okay, our trouble is how to understand it. Well, does the same thing still hold? What do you mean by e to the lambda t this time? That goes back to Euler's formula. So number 1, we decompose them into the real part times the imaginary part. And this part is easy. Now for the imaginary part, we use Euler's formula. That is e to the I theta equals cosine theta plus I sine theta. Have you guys seen this formula before? Okay. Basically, when you talk about how to represent a complex number, you have a plus bi. That's certainly one way. And we associate with that thing with a vector. For example, 2 plus 3i is nothing but 1, I, 2, 3. So this is the vector. Okay, that's the vector corresponding to 2 plus 3i. Good so far? We have the plus, we have the minus, we have the multiplication, which are all the weird rules. That's fine. But now you need to ask yourself, well, to represent a point, this is almost like represent a point with xy, right? I do have another way to do that, which is called rho theta. Same vector, but rho and theta. We call it polar coordinates. Okay. For that way, what you have here really is just cosine theta plus rho sine theta. That's how I got the xy, right? So this one coincident with what we had before. But we have a better way of writing it to be rho ei theta. The theta is the theta here, and the rho is basically how long that thing is. So basically, you're just representing a complex number using polar coordinates if you write them in this way. And then, of course, it's going to be the same as the xy coordinates because you're basically saying the same complex number. Sounds good? Okay, that's two representations. Why are they the same? Well, there are multiple ways of proving it. I will just offer you a really straightforward way. Do you remember e to the x? Okay. If you do the Taylor expansion, right? If you do the cosine x, do you remember the Taylor expansion of this thing? This one only have the even terms. And this one only have the odd term. Sounds good? Okay. Now, basically what you observe is basically cosine x and the sine x, all the exponents of them putting together will be just e to the x. Except one takes all the even term, one takes all the odd term, and they become oscillating. Not all positive. Positive, negative, positive, negative. Good so far? Now, if you think about that thing, what will happen if you plug in I theta here? Okay, it will basically have everything the same, except you replace x to be theta, right? Whenever you see an odd one, you have I. Whenever you see an even one, which means you have I squared or I to the fourth, you either have 1 or -1, right? So you can do the calculation yourself. I will skip it. I think it's not hard to see. By doing this, you will exactly pick all the ones without I and all the ones with I. They happen to be these three. So try by yourself. Sounds good? A third thing, which this formula becomes super, super nice, that is when you represent waves, usually people use a wave to be I times something. Let's just say I theta representation. Why? And here's why. Okay. You know how to represent a wave, right? Wave is just like cosine. Like that, right? Okay. This is called plane wave. But in 3 dimension, you don't have a plane wave. You have a wave in 3 dimension, which is like non-plane, which is 3D. What can happen? 2-way. You can shake the thing horizontally. So horizontally, you generate a wave. Good so far? At the same time, you can shake the thing vertically. Then vertically, this one also generates a wave. Still okay? What will happen if you shake horizontally, meanwhile you shake vertically? The 2 waves got combined. What do you think the shape will look like? Think about it. Horizontally, you have something. And let's say vertically, you have something. Horizontally, you have something. It doesn't have to be aligned with the face, but you see what I'm talking about? Horizontally and vertically, so you have something, that's right, going like this. I don't know how to draw it like this, but moving forward. That's what the most general form of wave you can see in 3 dimension. It's not plane wave anymore. If they happen to have the same frequency, you basically have something shaking at 45 degrees, it's still a plane wave. But if the frequency is a little bit different, then you won't have something like this. And if you look at it from the perspective, you basically have something rotating all the time, meanwhile going forward. Okay, so e to the I theta actually is how you represent wave in 3D. Because you do have a wave horizontally and you do have a wave vertically. And you plus them together, you have a superposition, which is horizontal and vertical together. Okay, that's enough of Euler's formula. So you have all these kind of ways to think about it. But the key is we have this formula. So that's number 1. Number 2, then your E lambda T really becomes, hold on, let lambda be A plus BI. Then your E lambda T really is E A plus BIT. Which is e to the AT times e to the BTI. I switch the order so you can see it's e to the AT times cosine BT plus I sine BT. That's the first decomposition. We have the real part and imaginary part. Then your YT basically have 2 parts. I will call this part Y real because you don't have an I. I will call this part without I Y imaginary. Both Y real and Y imaginary are real because I manually times the I here. So if you get rid of the I, everything here is just real. Okay, that's what we mean by Y real. It's a number. Y imaginary. It's a number. Okay. Then theorem. The theorem says the following: if Y can be written by the real part plus the imaginary part, okay, then both y real and y imaginary are the solution of if this one satisfies the equation. What do you mean by that? That means if you, like the system we just did, we have lambda equal to this, right? Then your solution yt is going to be e to the lambda t. Cosine 3t. Which is this is the real part. This is the imaginary part. Then your general solution is going to look like this. That's basically what the theorem says. So you saw the system. Okay, we haven't proved why the theorem is true. We don't know that. But once the theorem is true, do you see that we can already solve the system? Because it's a 2 by 2, you're just looking for two solutions, right? And then all the possible combinations will give you all the solution. Okay, this one tells you if you solve it, you have a complex number, automatically you obtain two solutions because one is real, one is imaginary. You already have two solutions. Moreover, they satisfy the equation according to the theorem. Number 3, they are always linearly independent. Can you see why? Because y is cosine, y is sine. Of course, they are always linearly independent. You plug in 0, you got them to be totally different. Sounds good? Okay, so for complex things, you basically just solve it and you have only one solution, which has two parts, which give you two solutions. And they are linearly independent. Sounds good? Okay, so the only thing we don't know yet is why this theorem is true. Okay, and we can do a quick proof. Why the theorem is true. So what we want is if y equals y real plus I times y imaginary satisfies y prime equals ay, then that basically means y real prime. Okay, then that basically means you can distribute the prime Good so far? What I'm trying to say is you have two complex numbers and they're the same. How can you make two complex numbers to be the same? That means their real part is the same. And their imaginary part must be the same. That's the only time two complex number is going to be the same, right? That means your real part satisfies this equation. And your imaginary part after you divide by I also satisfies this differential equation. Sounds good? So basically, why do you have two solutions? You use the hidden fact. That is, if this happened, this also happened. But the one will give you a solution in real realm, and the other one will give you a solution in imaginary realm. And they will always be linearly independent because one is real, one is imaginary. Sounds good? So when you allow complex numbers, you're basically solving the same differential equation for twice. And they got one answer each in two different realms. Okay, but that's the proof there. All right, next time we will teach you how to do the sink and the source thing for this. It's gonna be similar, but it's not gonna be straight anymore. It's gonna be a spiral in the phase plane. Okay. All right, that's all for today. Stay